So in this chapter, chapter number 4, we are going to look at how the operational amplifier circuits are going to be affected when you are operating them at different frequencies, which are not DC or close to zero. Like last chapter, we discussed the effect of the operation of operational amplifiers circuits when you are operating them at zero frequency, that is DC, or close to zero, that is very low frequencies. And we found out that even if you use the parameters which are ideal parameters that we usually use, infinite amount of open loop gain, infinite input resistance of the operational amplifier, and zero output resistance of the operational amplifier, still it gives you pretty much similar results as if we use the actual values of those quantities in a circuit. That is, if we use the open loop gain about 200,000 or something, and the input resistance of operational amplifier about what was that, like some mega ohm, forgot what was the actual value, 2 mega ohm to 3 mega ohm, something like that, and the output resistance was around 75 ohms or something. So even if we use those values, we still were getting pretty much the same result as assuming the ideal values. Now, in this case, in this chapter, when you got, what you're going to observe is that's really not the case, and the values are going to affect the operation, especially if you are operating the circuit outside the required bandwidth, or if you will see if the change in the input signal is too fast, that is, the frequency of the input signal is too fast as compared to what we call the slew rate of the amplifier. That is, it just cannot follow that speed of the input sometime for different operational amplifier circuit. There's a specific threshold that if the input is changing above that threshold, then the output, because remember, any signal that is traveling in a circuit through operational amplifier, it's going to take that signal some time to go from input to the output, right? If input is changing very fast, then it's possible that the output may not be able to follow that speed of the input signal. So that's also we are going to look at in this chapter, that what is the threshold of that frequency that you can give at the input such that the output could follow the input signal. So all those things we're going to discuss in this chapter. Closed loop frequency response. So we've been discussing closed loop gain since chapter number 2. We discussed the closed loop gain, of course, inverting, non-inverting, and all those amplifiers that we discussed. Here we are first going to look at the open loop gain as a function of the frequency, and then we're going to move on to the closed loop gain as the function of the frequency. So open loop gain as a function of the frequency. We discussed that the open loop gain of amplifier was op amp is about 200,000, typical value, 50,000 minimum value or something. But that open loop gain is also a function of frequency. And if you look at this equation represents the first order filter equation that we discussed in chapter number 1. If you remember the Bode plot, low pass filter, this is how the open loop gain basically it changes. So A naught is your actual typical value of open loop gain, and at any frequency f in hertz, A naught is going to change based upon what frequency you are using and based upon what is the cutoff frequency of your circuit. So in general, the open loop gain is going to be defined by this equation, that the open loop gain at any frequency f is equal to the typical value of the open loop gain A naught, which let's say is 200,000, divided by 1 plus j f over f1, f1 being the cutoff frequency where the magnitude of the open loop gain is going to become 70.71% of the peak value, which is A naught. Remember, this is a complex quantity, so it has a magnitude and it has a phase. Who is going to tell me what will be the magnitude expression for this? If I want to write down the magnitude expression, What will be the magnitude expression for this 4.1? Anyone in the back? Hold on, Chris. Yes. Yes. What is the magnitude expression for this? It's a complex number. How we going to represent the magnitude expression of this complex number? Yes, Rudy. No, you can tell me if. Yeah, go ahead. Yeah, you're right. So for that specific equation, how are you going to write that? The same. What you're saying is correct, but what about the expression? Yeah. Well, what you just said, you are on the correct line, but for this expression, how are you going to interpret what you were saying? Because magnitude, you know how to calculate magnitude. What you told me. Yeah, exactly. But here is a fraction, remember. It's not just x plus jy, it's a fraction. So how you calculate the magnitude of complex number given in fraction? Jonathan? Okay, what should I do with the numerator then? Say it again. No. It's a complex number given as a fraction. Yes. Again. Separate what? No, I'm just asking about magnitude. I'm not going into angle right now. What will be the magnitude expression? A naught square is going to be a naught if you take a square root of that. Okay, so if you have to write it, how are you going to write it? Tell me that. Okay. Anyone else? Ronaldo, go ahead. Mm-hmm. Okay. All right. So again, this we discussed like, I don't know, 100, 200 times before. Magnitude of numerator divided by magnitude of denominator. If a complex number is given in fractional form and you're calculating the magnitude, it's the magnitude of the numerator divided by magnitude of the denominator. Magnitude of the numerator is simply, it's a real number, so it's simply a naught. And magnitude of denominator is a square root of real part, a square plus imaginary part, a square. So again, I mean, we discussed it many times. There should not be struggle when I ask this question, guys. That's going to be the magnitude expression. And since we are on this topic, what will be the phase expression of this? How do you calculate phase of a complex number given in a fractional form? Yes. Okay, so if the number is given in fractional form, like let's say this number, how are you going to implement what you're telling me? What will be the expression? No, not the denominator over numerator. Imaginary over real what? Okay, so again, tell me the expression, the phase expression for that 4.1. What will be the expression? Okay, negative. Explain it a little bit. Yeah, I think your answer is correct. Explain it. Negative f or f1 is not in the denominator. What do you mean there? I don't see any negative f over f1. So, okay, so in general, once again, and I always say once again, and then later when I ask, it's the same thing. So I don't think it works, but in general, how do you calculate phase of a complex number given in a fractional form? You have a plus jb divided by x plus jy. How do you calculate phase of that in general? 2 plus 3y divided by 4 plus 6j. How are you going to calculate the phase of that number? Yes, go ahead. I don't see any omega over here. Or I don't see any omega and whatever I said or there. So I don't know where the omega is coming from. Well, right, but there is no JW, right? Whatever is given, tell me according to that. Arctan F over F1, okay, there's something missing. No. Okay, so my question was, in general, if a complex number is given in a fractional form, how do you calculate the phase of that complex number? Irrespective of what is given. If any complex number given in a fractional form, how do you calculate phase of that complex number? This should not happen every time I ask this question, guys, come on. And it's not just this class, in like many classes, you have done that. Taken with other professors as well. And I know like 4 or 5 know, and they're like sitting there and it's like, let me answer. But all right. Yurat, go ahead. Yeah.
Giving us a complex, for example, a number, a real number plus a number, that means you'll with the arc tangent or inverse tangent of the imaginary number over the real number.
Okay, and if a number is given in a fractional form, then? Mm-hmm.
Minus the arc tangent of the denominator.
Very good, excellent. So basically, if a number is given in fractional form, it's a complex number, is a phase of the numerator minus phase of the denominator. Right? And how do you calculate phase of a complex number? Arctan over imaginary part over real part. So write it down, guys. Come on, write it down. I mean, don't forget these things. Why do I have to spend 20 minutes on the same thing over and over again in every class? Angle of AJF is equal to angle of the numerator. Again, this is a real number, so the angle is going to be 0 because remember, the real numbers, they lie on the positive x-axis. If they're positive values, if they're negative values, they lie on the negative x-axis. So all the real numbers that are on the negative x-axis, their phase is 180 degrees. All the real numbers that are on the positive x-axis, their phase is 0 degrees. All the imaginary numbers that are on the y-axis positive, phase is 90 degrees. And here, phase is negative 90. And in between anywhere, you go arctan of imaginary over real. So in this case, phase of the numerator is 0. So 0 minus phase of the denominator, which will be negative tangent inverse of imaginary part, which is f over f1, divided by real part, which is 1. So it's simply f over f1. And that's what, I think, Alfred, that's what you said earlier. But this is the explanation. So, and this is going to be revisited over and over again. Make sure now, write it down, understand it, and if I ask you again, don't hesitate to answer this. Anyway, so this is the magnitude of the open loop gain at any frequency, f1 being your cutoff frequency. If I plot this, Bode plot and exact plot, of course, the straight line is the Bode plot, which is A0 until, and it's not given in the decibel, the y-axis is not in decibel. Or I should say the straight line is the ideal plot and the curved line is the actual plot. So it's going to go A naught until the cutoff frequency, and after cutoff frequency, it's gonna start dropping down. Again, if it's a body plot, it's gonna start dropping down with negative 20 decibel per decade. At the cutoff frequency, and of course the curved line is the actual plot, which shows you that at the cutoff frequency, the magnitude is going to drop down to 70.7% or 0.707% of A naught. So this is how the magnitude of the open loop gain behave when you are changing the frequency. There's an important quantity over here, which is this B. And this B is called unity gain frequency. Unity gain frequency. And as you can see, the value of this B, the frequency B, is when the open loop gain value become unity. And that's an important quantity which is going to come in other formulas as well. So B is the unity gain factor, unity gain frequency. Yes. Drop what? Below 1. Generally, again, if you keep increasing frequencies and the frequency become extremely large, I don't think it's going to go below 1. It could, but again, we just go to the unity gain frequency. That's our theoretical limit in general. Because again, it starts at a very high value, remember 200,000 or something. So even if you're increasing the frequency. Yeah. Below 1 means that you have a negative decibel value basically, because at 1 it's 0 decibel basically, right? So below 1 is going to be negative decibel values. It's possible, theoretically it's possible. I don't know if practically it's possible or not. Theoretically it's possible that you go below 1. Open loop gain is just basically an operational amplifier. It's not, even in the open loop stage, it's not going to be amplifying anything. Because at 1, basically, whatever the differential input, the output is going to be equal to the differential input. Yeah, it's going to be voltage follower, right? At the unity gain frequency. But if you go below, that means output is smaller than the input. It's not even amplifying or anything. But that is the important factor that is used. So even if it does go below 1, we don't really consider it even in the theory. 741, as we discussed in the last chapter, 200,000 is the typical value of the open loop gain at DC. That's a DC value, remember, or very small frequency. Unity gain frequency is 1 megahertz. So it's not that, this thing is not that high. At 1 megahertz, it goes down to 1. So if you go beyond 1 megahertz, it's just going to go below 1, basically. But remember, we don't really use open loop gain that much. We use closed loop gains. So if we plug in the value of A at the unity gain frequency, A naught over 1 plus J, F replaced by B over F1, and we calculate the magnitude, A naught over square root of 1 plus B over F1. And B over F1 is generally quite larger than 1. Quantity of B over F1, 1 megahertz divided by whatever the cutoff frequency is. So we ignore this one, and this will be equivalent to A naught over B F1 or A naught F1 divided by B. So the cutoff frequency of the operational amplifier is going to be, and remember the magnitude at unity gain frequency is 1. So this is 1. So 1 is equal to A naught F1 over B, which is right here. So F1 is calculated as B over A naught, which means the cutoff frequency at which the open loop gain is going to drop down to 70.7% of 200,000 is very, very small. That cutoff frequency is about 5 hertz. And that you can see that why at the AC signal, the frequencies, the cutoff frequency, the open loop frequency, open loop gain, and all those things are going to be much affected by the frequency rather than no effect when we are operating the circuit at DC. Because at DC in chapter number 3, we saw that there was really no effect. But even if you change the frequency and go to 5 hertz, your open loop gain drops down to 70.7% of the peak value already at 5 hertz only. And as you are increasing, then it will keep going down, as you can see in this picture. Now from this, of course, B is equal to A naught times F1. B is naught is equal to A naught times F1, and B is also called the gain bandwidth product. It's, of course, it's the unity gain frequency or unity gain frequency, but it's also called gain bandwidth product. Gain, of course, is A naught, F1 is the bandwidth or cutoff frequency. At even 5 hertz, the open loop gain has dropped down to 70% of 200,000, so 141,420. Now in chapter number 3, last chapter, it was established that the closed loop gain of any amplifier is given by, let me write it down a little bigger, ACL. We're going to put DC because we were interpreting DC values in the last chapter, or DC frequencies. Well, DC has 0 frequency, but we were examining the circuit at DC. And this is the equation from the last chapter that we wrote to calculate the actual value of the closed loop gain at DC. Kn being the noise factor, noise gain, and A naught is the open loop gain at DC. Now in this case, of course, A naught is changing based on the frequency. That means our closed loop gain is going to change based on the frequency as well. So closed loop gain at any frequency JF is going to be equal to the maximum value of the closed loop gain, which will be at DC. So this value, which will be at DC, ideal over 1 plus Kn over A naught, divided by 1 plus J F over BCL. And BCL is called the closed loop bandwidth of the circuit. At which, what's going to happen at BCL? Who's going to tell me? What's going to happen at the closed loop bandwidth as far as the closed loop gain is concerned? 70% of the ideal value or DC value of the closed loop, not the ideal, DC value of the closed loop. And ideal and DC are very close to each other, as we observed in the last chapter. So even if we are using ACL ideal over here instead of ACL DC, then it is perfectly justifiable, because again we calculated it last week and they were very close to each other, not much different. So at the closed loop bandwidth, the closed loop gain of the circuit, whatever circuit you're creating, the closed loop gain of the circuit drops down to 70.7% of its peak value, which happens at DC. And this is the equation. To represent it, again, is the first order low pass amplifier equation. BCL is given by B over Kn. That is the unity gain frequency divided by your noise gain. Therefore, at BCL, the gain as well as the output amplifier will be 70.7% of DC gain and the DC output. Determine the output of the following amplifier at 3 kHz, which is the operating frequency of, let me increase this. Let me see if this is All right, so if a circuit, something like that is given to you, and if I ask you calculate the output of the circuit, since the input is an AC signal, then what I mean is to calculate the output of the circuit is you're calculating the output as at the input of the frequency. If it is not given to you, that calculate the output at 3 kilohertz or 4 kilohertz, but an input is given to you like this 10 cosine 6000 pi t millivolt, then you are going to calculate the output at the input frequency of the frequency of the input signal. Remember, now if it is given to you the input is 10 volt sinusoid, calculate the output at 5 kilohertz. Then it's already given to you that you're calculating at 5 kilohertz, right? But if it is not given to you, then you have to look at the frequency from the input signal if the input signal is given in the time domain. If it's given in the phasor domain, then of course frequency is going to be spelled out for you, that frequency of the signal is this. So do not ask that at what frequency you are asking us to calculate. The frequency is going to be the frequency of the input, which is the operating frequency of the signal. So determine the output of the following amplifier at 3 kilohertz, which is the operating frequency of the circuit. Operation amplifier gain is given, open loop gain at DC is given 100,000. And unity gain frequency is 1 megahertz, which is B. So this, what type of amplifier is this? Who's going to tell me? It is an inverting amplifier. Your input is connected to the inverting input. So ACL, we're going to use this equation right here. ACL JF is equal to ACL at the DC divided by 1 plus JF over DCL. Now, once again, ACL DC, although in the last chapter, we calculated ACL DC to be ACL ideal over 1 plus Kn over A naught. But remember, A naught is given as 100,000. What will be the Kn value for that circuit? Let's calculate that. Yeah, for this Kn, we calculate, derive the formula. It was 1 plus Rf over R1, which will be Rf is 4K, R1 is, R input is 100 ohms. So 1 plus 4,000 over 100, that's going to be 40. So that's 41. So even if we take 41, then 41 divided by 100,000 is just going to be very small. Therefore, ACL DC will be essentially equal to ACL ideal. So we don't really have to go and put ACL DC over here. We can just write down, and this is equal to ACL ideal over 1 plus JF over DCL. BCL, the closed loop bandwidth, is unity gain divided by Kn. Unity gain frequency divided by the noise gain. Unity gain frequency is 1 megahertz and noise gain is 41. Yes. How much? 24.3 kilohertz. 24.3 kilohertz is our closed loop frequency. That means at 24.3 kilohertz, and what will be the ACL ideal? Of course, it's an inverting amplifier, so it's going to be RF over R input, negative RF over R input. We don't have to worry about negative sign right now because that just represents the relationship of the input-output waveform shape, inverting 180 degrees. But even if we include that, that's fine. So you have, so yeah, sorry. So at 40, the gain is 40 at DC, right? 4 kilo ohm over 100 ohms. At 24.3 kilohertz, that gain is really going to be reduced 70.7% of 40, right? So even you don't go that high of a frequency, only about 25 kilohertz, your gain is already down to that. So that's what you see, that the frequency is affecting gain of the amplifier a lot. And if you're not being careful, by designing the proper gain at the frequency at which you're operating the circuit, then you assume that, okay, I chose those resistor values and my gain is 40. And then you start operating your circuit at 25 kilohertz, and you're like, well, I'm not getting that gain. My output is much smaller than what I'm expecting. And the reason for that is going to be because the gain has dropped down to already 70% of the value that you designed the circuit for. So that's where we have to be careful about when we are designing the circuit for AC frequencies, for AC signals. We have to be careful about what bandwidth we are operating the circuit. So 24.3 kilohertz is the closed loop bandwidth, and we can calculate the gain of the circuit at the frequency is 3 kilohertz. So at 3 kilohertz, let's calculate gain of the circuit. ACL ideal, so that's going to be negative 40 RF over R input. Let me write down equation first. So negative RF over R input over 1 plus JF over BC. Now remember, this is complex number, so it will have a magnitude and it will have an angle. Three kilohertz over 24.3. So I'm just going to write down 3 over 24.3. Can someone give me the value of both magnitude of this and phase of this? Yes. How much? 39.7 is the gain, and the phases 173. 173. 173 degrees. Okay. And remember, gain doesn't have a unit. This is not in decibel. 39.7, 173 degrees. So the gain dropped down from 40 to 39.7 at 3 kilohertz, and the phase used to be 180 degrees, and it changed to 173 degrees. Let me know if you have any question so far. And make sure to do the calculation so that you know. Yes, Gloria? Say it again. That's okay. Yeah, you can round it off. That's okay. 172.6, you can write down 172.6. That's fine. Yeah. Oh, by the way, I saw someone taking like 4 or 5 significant figure after decimal. You don't need to do that. 2 figures are good enough, more than good enough. So don't go 3, 4, 5 significant figures after decimal. Okay, so this is our gain. Remember, we have to calculate the output, or we have to determine the output, not just the gain. So let's insert another slide here. Now we know that output over input, and I'm just going to write down in j omega or jf, doesn't really matter which one, is equal to ACL j omega. Or V out jf over V in jf is equal to ACL jf. It doesn't really matter because you're taking the ratio, so f and omega in the ratio cancel out. 2 pi cancel out. These are phasor quantities that I'm writing. So in the phasor form, 39.7173 is ACL. And our input in the phasor form, phase is 0. So it's simply 10 angle 0 degrees millivolt. That's millivolt. So that's millivolt. All right, when we're multiplying two complex number given in polar form, what do we do? Who's going to tell me? Multiplying two numbers given in complex number given in polar form, how do we do that? At the face, exactly right. So 39.7 times 10, 397 millivolt. So V out j omega, 397 millivolts, so 0.397, 0.397 millivolt is 0.397, and then phase are added up, so 173 degrees. Input is given in time domain, output must be given in time domain as well. So who is going to tell me what will be the time domain expression of the output? Very good. 397 cosine 6000 pi t plus 173 degrees millivolt, or 0.397 cosine 6000 pi t plus. And that will be the output of the circuit at 3 kilohertz. Right? Yes. 397, make sure you add millivolt. It's not volt, remember. Just add millivolt, that's fine. Doesn't matter. Guys, remember, any signal going above saturation is just going to be cut down by the saturation value, right? So anytime you are writing an output of an amplifier, and if you know the saturation level is 15 volt or 13 volt or 12 volt, and your output is coming out to be 20, 24 volt, do not write 20 or 24 volt if the saturation value is given to you. If it is not given to you, then you can just write down, the calculated value is this, but based on what the saturation level is, it's just going to be the output will be equal to the saturation value, right? So that it shows your understanding that 6,000 volt is not possible, because some people just write down 6,000 volt is the output. Yes, theoretically, calculation wise, it is 6,000, but practically it's not possible because it's just gonna flatten at the saturation. Yes, Europe?
Just to how did you already mention the 173 degrees was added to the degrees added?
Yeah, when you're multiplying two complex number given in polar form, you multiply their magnitudes and add their angle. Yeah. All right, guys, any question about this? Okay. All right, so next we are going to look at the rise time of a waveform. And rise time and fall time, they are generally used when the waveform is a square wave, a rectangular wave, and so on and so forth. But it can also be used for other type of waveforms. So how fast a waveform is rising? That is your rise time rising, and sometimes it is taken from 0 to 100%, sometimes 10 to 90%. So when an input signal of op-amp is a pulse or a step signal, so a square wave, pulse signal, a step signal, the output signal, of course, is supposed to follow that. But if the input signal goes from low value to high value, the output takes an exponential pattern to rise to the steady state due to the internal capacitor of the circuit. So if the input is going from, as a step signal, going from 0 to the peak value, the output is going to go from 0 to the peak value, but it's going to take some time and behave as exponential input going to a steady state value, which is the bottom figure. Rise time due to pulse signal is defined as the time when the signal rises from 10% to 90% of its peak value. So it's going to 10%, this is the 10% line right here, to 90%. This is the peak value right here. So the time is going to take from 10% to 90% for square waves or for pulse signal is the rise time. And it is inversely proportional to the closed loop bandwidth BCL. The smaller the BCL, larger the rise time is going to be, and vice versa. Rise time due to pulse signal is given by 4.6, equation 4.6, which is right here. And figure 4.3 show the graphical interpretation of that. So this is an important equation. And these equations will be given to you when I ask you a question, because again, these are not the one that, they are very specific under these conditions. So I don't want, I don't expect that people are going to memorize these. These equations are given to you. But you should know what rise time means basically. So this is the rise time due to the closed loop bandwidth. That's why it says TCL. There's also a rise time that you're going to see due to the slew rate. That's going to be TSR. This is due to the closed loop bandwidth. For pulse signal, how fast pulse signal is rising, based on that we are going to calculate how long it's going to take for the output to go from 10% to 90%, and that time is going to be the rise time of the output. And according to this equation, as you can see, 0.35 over BCL, and BCL is B over Kn, so it's 0.35 Kn over B. And the next slide is what I mentioned earlier, is the slew rate. For linear amplification, output must follow the input and should have the same shape as we discussed in chapter number 1. If you're amplifying any signal and if the output shape is changed, then it's no longer amplification. Output shape should be the same as the input shape. Phase can be changed, that's fine. Phase can be changed, but output shape should not change. Magnitude can change, of course, because you're amplifying the signal. Again, op-amp, we saw earlier, op-amp internal circuit diagram, you have a bunch of capacitors, you also have a bunch of BJTs, and all BJTs, their base collector junction and base emitter junction, they act as, they have a small capacitors in there. So you have capacitors inside operational amplifier, and these capacitors need to charge and discharge as your input signal is changing. And it takes time for the capacitors to charge and discharge. So that charging and discharging of capacitor, they pose a limit on the rate of change of the input signal such that the output signal can follow the input signal. And this limit is called slew rate limitation. If this input is changing too fast, as I mentioned earlier, it's possible the output may not follow that speed, and change output frequency can change. That means the shape can change. Slew rate is represented by uppercase S, and it shows you how fast the output of an op-amp is capable of changing for a changing input. And we represent it as voltage per second, or the common unit is voltage per microsecond, because the change is happening quickly. The standard value of 741 I see that you used for slew rate is 0.5 volt per microsecond. 0.5 volt per microsecond change can happen for 741. And if it is faster than that, then 741 is not going to support that, which poses limit to the utility of 741 in faster applications. So if it is much faster than that rate, then 741 you cannot use. You have to use some other operational amplifier that has a smaller value of slew rate. If input is a pulse signal, the rise time due to slew rate is given by that equation. So there are two rise time, as you can see. One rise time is due to the closed loop bandwidth, and one rise time is due to the slew rate. And again, the subscript denotes which rise time you're talking about. So rise time due to the slew rate is output voltage over the slew rate. Rise time due to slew rate is different than the rise time due to closed loop bandwidth. Both conditions must be satisfied for any pulse input in order for the output to properly follow the input. So you have to satisfy both TCL and TSR for any pulse signal or square wave in order for the 741 or any operational amplifier to be used for that input pulse signal. For the slew rate, rise time goes from 0% to 100%, as you can see. The output is changing from 0 to the maximum value. Whereas for closed loop bandwidth, it goes from 10% to 90%. So this is another discussion that's going to come up as which one you're going to see. So the concept of slew rate, observe that for the rise time due to slew rate, we consider going from minimum to the maximum rather than 10% to the maximum value. Minimum. If an input signal is changing slower than TSR, if the input signal is pulse, it is changing slower than the value of TSR, this value, the output can follow it. But if it is changing faster than TSL, the output cannot follow it. And an example is given here. So this is an input signal in figure A, figure 4.5A. It is changing slower than the value of TSR that we calculate for that specific output over S. S, of course, is 0.5 volt per microsecond. And output depends on the circuit. You calculate the output based on the circuit. And the output is going to look like exactly the same as the input signal. The only difference is going to be that it's going to be magnified. Peak value is going to be magnified. ACL times V input. Here ACL times V input, which is the output. So this is the output. Divided by the TSR. So this is the time, rise time. So this is your rise time TR. V out over TR is less than the slew rate. Therefore, the output and input shapes are exactly the same, except the output is an amplified version of the input. In figure C and D, that's not the case. Input is rising up much faster, as you can see. And the output, the TSR value, is smaller than the input rise time. So the input rise time is given as Ti. This is Ti. And Ti in this case is much smaller than the slew rate time. So it's quicker than the slew rate time. And as you can see, the minimum it can do, minimum the output can do is going to take at least TSR second to rise, slew rate time to rise, because that's the minimum time it's going to take to rise. But the input time, rise time is much faster than that. Therefore, the input and output shape, they are different from each other now. And in this case, the output is really not following the input as it should, as you can see in A and B. So again, we have to be careful that the pulse that you're using, its rise time is at least equal to the slew rate rise time of the operational amplifier. If not, then the output is not going to follow the input properly. Yeah. How you control TSR? So if you look at the TSR, it depends upon two things, V out and S. So V out, you are controlling it based upon the gain of the circuit and everything input. And S is given 0.5 volt per microsecond is for 741, right? Now, if your output over, again, S, you calculate your TSR, and it turns out that TSR is larger than the input rise time for the input signal, then either you change the gain of the circuit or you choose another operational amplifier for which the slew rate is such that its TSR becomes smaller than your input signal rise time. How you calculate it? So generally, well, you can measure it on the oscilloscope basically, right? So you can measure it on the oscilloscope to see when it is going, input signal is going from 0% to 100%, let's say, right? You have to reduce the precision to be very small if the, because that's going to be quite a small time, but it's observable, especially if you want to do like simulation and stuff, and you increase your, or you decrease your the what you call the step size of the x-axis, then you can see how it is rising up. If you keep it bigger, then it's just going to rise up like a straight up, and you won't be able to observe that. So that can be observed. So again, this is just an example of to show that what TSR is going to play, the role that TSR is going to play in order for the output to be either a faithful replica of the input, just amplified, or not. So you have the TCL and TSR. You have to satisfy both conditions for a pulse signal. What if your signal is not pulse? What if your signal is a sinusoidal waveform? So we already discussed what's going to happen with the sinusoidal waveform. We did one example. If you have sinusoidal signal, how the gain is going to be changed based on the frequency. Closed loop bandwidth, basically. Now, if your input is sinusoidal waveform, how the slew rate is going to affect the value of the gain. Let's look at that now. So if the input signal is sinusoidal waveform instead of a pulse signal, slew rate imposes a limit on the frequency of the input sinusoid such that output signal can follow it linearly. If the output signal is given by a simple sinusoidal waveform with the peak value V out, then the rate of change of the output is going to be dV out over dt is going to be omega V out cosine omega t. Omega V out cosine omega t. And the maximum rate of change is going to be the maximum value of this, which will happen when cosine is 1. So the maximum value is going to be omega V out. So in order for the output to follow the input sinusoidal, the slew rate must be equal or greater than the maximum rate of change of the output. So the slew rate has to be greater or at least equal to the rate of change of the output. Because remember, slew rate is given in volt per second or volt per microsecond, which is the rate of change of the output signal, dV over dt. So S must be greater than or at least equal to omega V out, which is the peak value, which is the maximum value of the rate of change of the output voltage. Let FSR be the highest frequency at which the output can track the input signal. Due to slew rate limitation, this frequency is called slew rate limiting frequency, FSR. And the value of FSR can be found out with S greater than omega naught. Omega, of course, is 2 pi F. So FSR, if this F is the limiting value, FSR, it has to be equal to S over 2 pi V naught. So this is the highest frequency at which the output signal can follow the input signal. Any frequency higher than that, the output shape is going to change. That is, the frequency of the output is going to change. So input and output are not going to be exact replica of each other. So there are 4 things now, just to recapture. There's a lot of information we capture. There are 4 things. If your input has a sinusoidal waveform, you have to be careful about 2 things. You have to be careful about the slew rate frequency, that the input frequency must be smaller than, or at least theoretically equal to, the slew rate frequency in order for the output to follow the input signal. That's one. The second thing is the closed loop bandwidth, because when you're operating your circuit at some frequency, you're setting the gain of the circuit, whatnot, then make sure that you're operating the circuit way small at the frequency which is way smaller than the closed loop bandwidth. Because what's going to happen at the closed loop bandwidth? Gain of the amplifier is already down 70.7% of the peak value of the gain, right? So if you set the gain at 10 and your operating frequency is close to the closed loop bandwidth, then your gain is going to be down. Likewise, if the frequency is much faster than the slew rate, again, your output cannot follow the input. So you have to be careful about both conditions, that your frequency has to be much smaller than the closed loop bandwidth, and your frequency has to be smaller than FSR. One is much smaller. Why one is much smaller? Because at BCL, your gain is already down 70.7%. So it has to be much smaller than BCL, your operating frequency. And for FSR, it has to be just smaller, because as long as it is just smaller than this, the output can follow the input, right? So that's not a condition of that the gain is going to be down or whatnot. This is for the condition that the shape is the same as the input. For the closed loop bandwidth, the problem is the gain. The shape may be the same, but the gain is going to be different. So for the sinusoidal signal, we have to take care of both conditions. Any frequency that can satisfy both conditions, that's going to be the frequency that you can use for your circuit. If your signal is pulse signal instead of sinusoidal, then again you have to be careful about both TSR and TCL. Both TSR and TCL. And you have to satisfy both conditions. So we're going to do examples to show you how we're going to satisfy both conditions for both sinusoidal signal as well as your. Let's do this and then take a break. A digital signal has level 1 corresponding to 6 volt. This is your digital signal. This is level 1, this is 0, this is 6 volt, and this is 0 volt. What should be the minimum rise time such that the output signal would be undistorted due to slew rate restriction if 741 is used? Since we are looking at the slew rate restriction, we are going to calculate the rise time due to slew rate, TSR. And TSR is V naught over S. In this case, V naught is 6 volt and S is 0. So the 6 volt, 0.5 volt per microsecond. So 6 divided by 0.5 is 12 microsecond. So 12 microsecond is the minimum input pulse rise time required in order to in order for the input, in order for the input, for the output to properly follow the input pulse. If your input rise time is smaller than 12 microseconds, then the output is not going to be able to follow that pulse, because it requires at least 12 microseconds for the output to go from 0 to 100%. All right, guys, let's go ahead and take a break and then continue from here after the break. Okay, guys, so the next example, we are going to calculate the maximum value of the input frequency if the signal is sinusoid, such that we can satisfy the condition for the slew rate. So if the output signal in 4.2, the one example that we did earlier, this, if the maximum signal, if the output signal is sinusoidal signal with the peak value of 6 volt, determine the maximum input frequency due to the slew rate. So the output signal is a sinusoidal signal with the maximum value of 6 volt. This is the output. And we want to know what should be the input frequency maximum value such that the output can properly follow the input signal. So going to back to the slide, this slew rate has to be greater or equal to omega v naught, and then we did the derivation. And the maximum value of the input frequency due to the slew rate must be the maximum value inequality is S over 2 pi v naught. So we're going to use this. FSR is equal to S over 2 pi v naught. S over 2 pi v. So slew rate is for 741 is 0.5 volt per microsecond, and then V naught is 6 volts, so that's going to be 12 pi. Volt. Calculate. Now, sometimes students make mistake over here. Remember, this is 0.5 volt microsecond. So you have to divide 1 exponent -6 second divided by 12 pi volt, because it's going to be hertz. Frequency is going to be hertz. So volt and volt will cancel each other, and it's going to be 0.5. 1 over second is going to be hertz, basically. How much? What's the result? 13.2 kilohertz. So the explanation is the maximum input frequency cannot exceed 13.2 kilohertz in order for the output to follow the input signal. due to slew rate restriction. Due to the slew rate restriction. So this is the maximum frequency that the input signal may have. If it exceeds that value, the output frequency is going to be different than the input frequency, and the shape is not going to be the same. Make sense? Okay, now we're going to combine both. As I mentioned earlier, you have two conditions for the pulse signal, TSR and TCL. And you have two conditions for the sinusoidal signal. You have BCL and you have FSR. So we have to satisfy both conditions for each type of signal in order for the output to faithfully follow the input, first of all, and second, our gain of the circuit is maintained, the one that you're setting for. So if the signal is a sinusoidal signal, then the highest frequency of the input signal, it has to be quite smaller than BCL, and the highest frequency has to be smaller than FSR. And again, I explained it has to be quite smaller because again at BCL the gain is already down 70.7%. So you don't want to operate a circuit close to BCL. It has to be much smaller than the closed loop bandwidth at which you want to operate the circuit. And that's why it says quite smaller, less and less, basically quite smaller than BCL. On the other hand, it has to be just smaller than FSR because there's a limiting condition at which the output can follow the input shape. So if the highest frequency is just smaller than FSR, that will work. So the first condition is quite smaller and the second condition is just smaller. So we can calculate both frequency due to BCL and frequency due to FSR and then decide what should be our operating frequency for the circuit. Likewise, if your input is a pulse signal, a step voltage, a square waveform, then you have to satisfy the condition for the input rise time for both TCL, the closed loop, due to the closed loop bandwidth, and TSR due to the slew rate. And the input rise time has to be much greater than TCL, and the reason is because TCL is measured from 10% to 90%, so it's a smaller time, whereas TSR is measured from 0% to 100%, so it's a larger time. So we're going to target the one that is smaller, that it has to be quite larger than the one that is TCL, and TI has to be just larger than TSR. So TI must be quite larger than TCL since the rise time TSL is a smaller quantity. Time it takes for the pulse to go from 10% to 90% of the peak value, whereas TSR is the time that covers the whole range of the output pulse. And we have those equations, of course, we discussed those equations, 4.6 and 4.7. Yes? It's a frequency we consider for sinusoidal signal. For the pulse signal, since they're going from 0 to 1, we consider the rise time. But for the sinusoidal signal, we consider the frequency, how fast it is changing. How fast it is changing, yeah. Because the rise time is generally considered with the signals when you have the step signals or square wave, rectangular wave, basically step signals. Then we consider rise time. Yeah. Frequency is for sinusoidal signal. For the following inverting amplifier, again, it's hard to see, so let me increase it. Investigate the value of the highest input frequency for the linear operation. 7/4 operational amplifier is used. Again, it's a sinusoidal signal. That means for the linear operation, and linear operation, again, it's combination of both, that the output gain, of course, is linearly dependent on the gain that you're setting. I mean, the gain of the amplifier is linear. Output times the gain should be equal to the input voltage. And of course, the output shape also linearly follow the input shape. In this case, we have to investigate frequencies for both conditions. And the first condition is that the highest frequency of the input, FH, observe I'm not giving you any frequency over here. I'm just putting omega t. Both conditions should be satisfied. All right. So FSR is S over 2 pi V naught, and BCL is B over Kn. These are our equations. Now, BCL does not, as you can see, it does not depend on anything except the constant value of B, which is 1 megahertz, and the value of Kn, which depends upon your resistors. So it's going to be constant irrespective of what is the input signal, what is the output signal. FSR depends on the output signal. Of course, S is constant for 741, but output is going to change based upon the input. So FSR can change, but BCL is going to stay constant as long as you're not changing the value of RF and R input. So let's calculate BCL first. B is 1 megahertz for 741. And Kn is going to be 1 plus RF over R input, so 40 over 4, which will be 10. So 1 megahertz over 11. Or 98, 90.95 watt. What hertz, kilohertz, megahertz, kilohertz? 90.9 kilohertz. So this is one of the frequencies that, and we want the highest frequency to be much smaller than this, because at this frequency the gain is going to be down by 70.7% of the DC gain. Now FSR. Okay, V naught. What will be the output of this circuit? Who is going to tell me? And again, we just need the magnitude. We don't need, because it's an inverting circuit, you don't need to put negative sign. 20 millivolt is the input. Gain of the circuit is 10. So 20 millivolt times 10 is going to be the output. S is 0.5 volt per microsecond. 2 pi 20 exponent negative 3 times the gain, which is 40 over 4, 10. And that's calculator. Yes. How much? 0.8 megahertz, so 800 kilohertz. 800 kilohertz? No? What you guys are getting? You're not getting 800 kilohertz? What you getting, Chris? 397? Anyone? 800 or 397? 397? Check. Let me do it. You got it? 397K? Okay. So 397 kilohertz. So there are two values. What do you suggest? What should be our highest frequency of the input signal in order for the output? Forget 2 pi. Okay. All right. What should be? Because these are two conditions, right? Your frequency cannot have two values. Your frequency need to have one value. But we are not finding the exact value here, remember. We're just finding the condition that the frequency has to be much smaller than this in order to satisfy both conditions. So what it is going to be? Yeah, 90.9 kilohertz, because of course this is a larger value and it has to satisfy that it must be much smaller than BCL and FH must be smaller than FSR. So if it is much smaller than 90.9, then it will satisfy both conditions. Let's write down here. FH must be quite smaller than 90.9 K to satisfy both conditions. So that's another thing that I have observed that some of the students do, that they do calculate this, but they don't mention that which one need to be chosen in order to satisfy conditions. So make sure do not forget that, because you cannot have two frequencies. Remember, signal will have one frequency. So once you calculate these values, make sure you mention clearly that which one you're going to choose, what will be the condition in order to satisfy the slew rate requirement as well as the closed loop bandwidth requirement, both of them. Any question about this, guys? No? Okay. All right, now we are going to look at the condition. Example 4.4 with the peak input voltage of, so same signal, sinusoidal signal, but now the input voltage is 100 millivolt instead of 20 millivolt. So this is our V input. BCL is not going to change because it is not dependent on the input voltage. So BCL is still going to be 90.9 kilohertz. Independent of the input voltage. FSR is going to change. S over 2 pi V naught, 0.5 volt per microsecond over 2 pi. And in this case, input is 100 millivolts. So 100 milli times 10. Gain is, of course, RF over R input, which is 10. Yes, 79 kilohertz, 79.5 kilohertz. So in this case, what do you suggest? Which? Again, there's no. It has to be smaller than that. It has to be smaller than that. Yeah, it has to be smaller than 79.5 kilohertz in order to satisfy. I would say 79 and 90 is only 10 kilohertz difference. So I won't operate it at 79 because it's still very close to BCL, only 10 kilohertz difference, right? I would still go below 79, maybe somewhere 65, 60 or something like that, to be very honest, if you do not want to disturb your gain. Now, the other thing is, if you're designing your circuit for a gain of 100, at DC, let's say you design the circuit for a gain of 100, but you calculate, you do the calculation, and you're like, well, oh, my BCL is 90.9, I'm operating at 60 kilohertz. So instead of designing at 100, you can actually design at a higher gain such that when you operate it at 60, the gain becomes equal to 100 or 10 or whatever you're designing for. So at DC, design it for a higher value of gain, right? But if at DC you're going to design for 10 or whatever, then definitely at 60 kilohertz, it is going to be, it's not going to be 70.7% of peak value down, but it's still going to be down a little bit. It's not going to be exactly 10, maybe 9 or 9.5 or something. Based on the equation that we have, we can calculate the exact value of gain at that. So we can basically calculate what should be the gain at DC in order to have a gain of 10 at 60 kilohertz. Let's say if your operating frequency is 60. But in this case, the condition that we will set, of course, that it has to be smaller than 79.5 because 90.9 is still greater than 79.5. FH must be smaller than FSR, that is 79.5 kilohertz, in order for the output to linearly depend on the input. All right, next example. The input to a non-inverting amplifier is 20 millivolt pulse signal. So there is a pulse signal, and the peak value is 20 millivolt. This is 0. Investigate the limit on its rise time to produce a linear output. So now we are looking for that. What will be the rise time of the input signal Ti, such that the output can linearly follow the input. So Ti has to be quite larger than the rise time due to the closed loop bandwidth, and Ti has to be larger than the rise time due to the slew rate. Both condition needs to be satisfied. Closed loop bandwidth rise time, the equation was given earlier, was discussed, was V naught over S is the slew rate, and where's that equation? 0.35 over BCL. Okay, 0.35 over BCL. 5 over 0.35. BCL is B over Kn, so Kn over. All right, what is the values? 1K and 40K. This is 1K and this is 40K. So 0.35 Kn is going to be 1 plus RF over R input, so 40 over 1, 40. And B is 1 megahertz for 741. 0.14 microsecond. 0.14 microsecond, so 140 millisecond. 0.14. Anyone wanna check if the result is correct? 0.14 microsecond. 0.014 microsecond.
Yeah.
14.35 microsecond, not 0.14. Andre, you're getting the same? You're getting the same? You know, check your values. Okay, let me check. Zero point 0.35 times 41 divided by 6. Yeah, 14.35 microsecond. 1.435 exponent negative 5. 14.35 microsecond. Okay, and then so this is TCL. Now TSR is equal to right here, V naught over S. V naught over. All right, output voltage, input to non-inverting 20-volt pulse. Okay, so output voltage is going to be the peak value times the gain. So the peak value is 20 millivolt. And the gain of the amplifier, since it's a non-inverting amplifier, the gain is going to be 1 plus RF over R1. So 1 plus 40 divided by 0.5 volt per microsecond. Yes. 1.64 microsecond. Is that the correct result? Yes. Okay. So what do you guys suggest? Which value we are going to use as our limiting case? So Ti has to be much larger than TCL, and Ti has to be larger than TSR. Now TCL is 14.35 micro. This is 1.64. So the input has to be larger than this, and if it is, then it will automatically be larger than this. So in this case, Ti must be quite larger than 14.35 microsecond to satisfy both conditions. And once again, this is important that you that you write down this statement as what will be your time that you will choose in order to satisfy both conditions. Don't just calculate time and leave it, as many students do. Questions? Anything that is not clear? And remember, we're not having quiz from this chapter, so make sure you understand everything properly. Of course, there's a homework, but if there's any question, make sure to do clarification. There's a lab from, I think, lab number 3 is from this chapter. I don't think we are discussing that today. Okay. Yeah, that's it. Okay. Oh, so lab 3 and 4 we are doing together on March 3rd. Okay. Okay, guys, let's move on then. If there is no question, we have a few more things that are left. A discussion of noise in operational amplifier. What type of different noises are present in operational amplifier, and how to calculate the noise gain that we've been discussing. That's how you're going to calculate that noise gain, because that is the gain of the output noise versus the input noise, or that's the ratio between output noise over input noise. So there are 4 broad categories in which you divide noises, different type of noise. In op-amp or in general, the noise is divided into 4 categories. You have the thermal noise due to the random motion of electric, that should be charges, not changes, electric charges. And it increases as temperature increases, because the movement of charges, when they get at high temperature, the movement increases and they hit each other more frequently. So the thermal noise rises as the temperature rises. It's also higher for larger values of resistors. You have Poisson noise, also called short noise, random fluctuation of current, which is due to the discrete nature of electric charges. You have a pink noise or flicker noise that occurs at low frequencies due to the resistant fluctuation in electronic devices at low frequencies. It is also called 1/F noise, and it has higher power density at low frequency. So the noise basically occurs at lower frequency. At higher frequency, you don't really have that much of a pink noise. And then we have burst noise, also called popcorn noise. And that is due to the momentary change in the input bias current, which is due to the imperfection in the semiconductor surface. And again, it happens at low frequencies, less than 100 hertz. So both 3 and 4, they are at low frequencies. Thermal noise can happen at any frequency. It depends on the temperature. And short and Poisson noise, again, random fluctuation of the current can happen at any frequency. Thermal and short noise have Gaussian distribution, and they fall under the category of white noise or Gaussian noise. So first and second, they are part of Gaussian noise or white noise. And there's a web page link here, and you can get a detailed explanation of noise in operational amplifier circuit from Texas Instrument, basically. I found it to be really good. Discuss all different type of noise. Even they have one more, avalanche noise. So if you are interested, just go over that. It's a pretty long description, pretty long paper. So I'm not going over it, but it has equations and stuff that we don't really need, but some explanation as well. How do we model the noise for operational amplifier? That's the circuit to model the noise. You have the input noise, V noise input, and you have the output noise, V noise output. So if noise is modeled as a voltage source connected to the non-inverting input terminal, then what is the output noise that you're going to observe based upon the gain? Then that gain is what? Is the noise gain, Kn, that we've been using. That is what the noise gain is. And how do you calculate that? Generally, the noise characteristic curve, one of which is shown in figure 4.8, and on the next page, which is appendix C in the textbook. Total noise referred to the input is calculated for input resistance for a specific bandwidth, and then output noise is calculated. And again, those curves are here as well, these type of curves. They are given in the book, the one that I'm going to show you on the next page. And from there, we are going to calculate the total output noise for any input noise and calculate the noise gain value. It's quite a small, I just copied from the book, basically, this example. So this is figure 4.8 in the appendix C of the book, broadband noise for various bandwidths for 741 operational amplifier. There are different frequency bands given to you, 10 to 100 kilohertz, 10 to 10 kilohertz, and 10 to 1 kilohertz, 10 hertz to 100 kilohertz, 10 hertz to 10 kilohertz, and 10 hertz to 1 kilohertz. Y-axis is total noise referred to the input, RMS value, microvolt RMS value, and then x-axis is the source resistance. So 100 is starting at 100 ohm and going all the way up to 100 kilo ohm. And y-axis is total noise referred to the input in microvolt RMS. Consider a non-inverting amplifier circuit shown in this. So this is your non-inverting amplifier, 100 kilo ohm is RF, and our input is 100 ohms. And you have a resistor connected over here, biasing resistor or something. Oh, this is the noise resistor for the 1K, basically this 1K. Consider the non-inverting amplifier shown in this. It is desired to estimate the total noise level in the bandwidth of 10 hertz to 1 kilohertz. So 10 hertz to 1 kilohertz is the bottom one, this one. Determine the total RMS noise referred to the input. Determine the corresponding output noise level. So we're going to assume that the major contribution to external noise is from 1 kilo ohm resistor, which is this right here, connected at the non-inverting input. From the curve, basement noise for this basically this curve, the input RMS noise for source resistance 1 kilo ohm is estimated to be 1 microvolt. So you're going to take 1 kilovolt and you're going to look at the value for the total noise referred to the input, and that is 1 microvolt RMS value. So that's your input value of the noise, 1 microvolt. That's part A. Determine the total RMS noise referred to the input. Determine the corresponding output noise level. So the noise gain for the circuit is equal to the closed loop voltage gain. It's a Kn value is 1 plus Rf over R input, as we know, which is going to be 1 plus 100K over 100, so 1001. So if you're calculating the output noise for the input noise value of 1 microvolt, output gain, noise gain is 1001, and input noise RMS value is 1 microvolt, so the output noise will be 1 millivolt. And that's the RMS value of the output noise. So again, a small value as compared to our regular output voltages that we usually see. So it's not going to really affect the output voltage because the value is just so small, but it does exist. If your input signal is small, then yes, you have to be careful about. If your output signal is small, you have to be careful about the effect of noise as well, because it's going to combine with the output signal and distort the output signal. In general, if the output values are high, then this noise is not going to do much to the output. So this topic is just for understanding that the noise concept in operational amplifier, and actually what is Kn. I know how we calculate Kn, the noise gain, but what exactly is Kn? So it's a noise gain. It's a ratio between the output noise to the input noise for any band of over any band of frequency for a specific value of the resistance connected to the input. That's what Kn is, noise gain. All right, guys, last topic is common mode rejection ratio. Every differential amplifier, including op-amp, remember operational amplifier is a differential amplifier. It amplifies the output based on the difference of the voltages that you apply at the non-inverting terminal and the inverting terminal. So it's a differential amplifier. So every differential amplifier has two types of gains. You have a differential gain and you have a common mode gain. Differential gain, of course, is whatever the difference of the voltages at the input multiplied by the gain of the amplifier is going to be the output. That's the differential gain. AD is the output differential voltage divided by the input differential voltage, or output voltage due to the differential input voltage. Differential gain has been discussed. Okay, so far we have given the gain of an input as an open loop gain A. In this section, we will differentiate it from the common mode gain, which is called and call it differential gain. So this is, so far we assume that this is equal to A, because if you're using the operational amplifier in open loop configuration, then we assume A is the open loop gain, and whatever voltage you apply here, that voltage multiplied by A is going to be the output voltage. Here we're going to differentiate it with the common mode, so we're just going to call A as AD. It's the same thing as A, but we're going to call it AD. Now, what is common mode? Common mode is if you apply the same signal at both inputs. So you have voltage that you can see, VCM, common mode voltage, and that voltage is connected to both inverting input and the non-inverting input. What should be the ideal output? If I ask you, what should be the output if you apply same input at both inverting and non-inverting, what will be the answer? Ideally, it should be 0, right? Because operational amplifier amplifies the difference of the voltages at the input, right? So ideally, it should be 0 because it's the same voltage that you're applying. Now, practically, it may or may not be 0. Common mode gain is given by, if you apply the same signal and observe the output, the ratio between the output for the common mode to the input voltage is the common mode gain. Now, as again, ideally it should be 0, but practically it is possible that you have a value. Ideally we should get 0, but practically it is possible that gains of inverting and non-inverting inputs are slightly different. Remember, each input, there's a differential amplifier at each negative and the positive, or their BJTs basically at both of them. So due to the imperfection in BJTs, it's possible that you may have slightly different voltages at the input, even though you're giving the same value. Internally, there may be a slight difference between the voltages. It is possible that we get an output voltage, although ideally the output voltage should be 0. But again, there is a possibility that you have an output voltage. So if you do have an output voltage, then you can calculate the common mode gain, which is output voltage over common mode input. And then we can calculate the common mode rejection ratio, which is the ratio between the differential gain and the common mode gain. Now, once again, ideally, it should be infinity, because if ACM is 0, because your output voltage, if you apply the same input at both inverting and non-inverting input. If your output voltage is 0, then ACM is going to be 0. And ideally, it is going to be, if ACM is 0 because output is 0, then ideally this should be infinity. So ideally right here, I wrote down. Ideally, CMRR should be infinity. But practically, again, it can be different because CM may have a small value. May. In fact, for 741, CMRR is 70 decibel minimum and 90 decibel typical. That means your ACM does have a small value such that this value of CMRR is in the data sheet of your 741. It is inversely proportional to the frequency. The higher the frequency, the smaller the CMRR, and vice versa. And it is used to calibrate instrumentation amplifier to make sure that both input terminals are balanced. So that is why we use it for. For a certain amplifier, differential gain is 100 decibel and CMRR is 70 decibel. Determine the common mode gain of your circuit. So AD is 100 decibel, CMRR is 70 decibel, and ACM is what we need to know. So CMRR is AD over ACM, and if we go in the decibel scale, CMRR decibel, 20 log 10 of CMRR, 20 log 10 of AD over ACM, which will be 20 log 10 of AD minus 20 log 10 of ACM. Twenty log 10 of AD is simply the value of AD in decibel, and 20 log 10 of ACM is the value of ACM in decibel. So every value is given in decibel, so we can calculate ACM in decibel, which will be equal to AD in decibel minus CMRR decibel, which will be 30 decibel. What about the linear value of CMRR, not the logarithmic value? How are we going to calculate that? Yes, how are we going to calculate the linear value instead of logarithmic for ACM? Say it again. 10 raised to 30 or 20, exactly. This formula, remember, this is your ACM decibel. ACM decibel. All right, what is the result? 10 to the power 1.5 is 31.6. So observe that it's a significant gain actually. It's not close to 0, 31.6. We expect it to be very close to 0 or 0 ideally, but it's a pretty significant gain. All right, guys. So this concludes this chapter.